Welcome to The Explainer. Today, we are diving into one of the most important, truly foundational technologies behind modern AI, the vector database.
You know, every single day, we're generating this absolute mountain of data. Photos, documents, songs, you name it. But here's the thing. For a traditional computer, all the deep meaning, the context, the feeling behind that data, it's pretty much locked away in a box. It can't open.
So what if you could actually search for that feeling in a picture? Or, the concept buried inside a huge document? Well, that's exactly what we're going to explore. The tech that lets us search not just for keywords, but for the actual ideas and the context hidden inside our data.
Okay, so to really wrap our heads around this, let's start with a problem. A really big one, actually. The kind of problem that traditional databases, they just completely fall short on.
So imagine this. You've got this absolutely gorgeous photo of a sunset over the mountains. It's stunning, right? Now let's say we want to save it, but in a regular old school database. Now, a traditional database, it's not totally useless. It's pretty good at the basics. It can store the image file, the binary data. It can hold on to some simple metadata, like when it was created. And of course, any tags we add by hand, like #sunset, #landscape.
But here's where it gets tricky. With just that information, how on earth could you search for something like serene landscapes or pictures with a warm vibe? The short answer is, you can't. Those concepts, those feelings, they just don't exist in those simple little data fields.
And this fundamental disconnect, it actually has a name. It's called the semantic gap. It's this chasm between how computers store data in neat, structured boxes and how we humans understand it with all its context and nuance and meaning. And that gap is the exact problem that vector databases were invented to solve. So how do we build a bridge across that semantic gap? Well, the answer is genuinely fascinating. We have to start thinking about our data in a totally new way. We have to translate its meaning into the universal language of math. Yeah, so instead of relying on just simple tags, we use AI to transform all that messy, complex data, like an image, into a simple list of numbers. And the special list of numbers, this array, is called a vector embedding. Think of it like a numerical fingerprint that captures the essence of the data.
And this is where it gets really cool. Look at how these numbers, these vectors, actually capture meaning. For a mountain sunset, the vector might have a really high number in the elevation dimension. For the beach sunset, that same number would be super low. But see how the number for warm colors is really high and similar for both? That is how the database can understand that these two totally different pictures are, in a way, very similar. It's all in the math.
And hey, this whole concept isn't just for pictures. Not at all. We can turn almost any kind of unstructured data into these meaningful vectors. We're talking text documents, audio files, pretty much anything you can think of. All right, so you're probably wondering, how does this magic actually happen? How do we go from a picture to a list of numbers? Let's pull back the curtain on this embedding process.
Okay, so it starts by feeding the data, say our image, into a specialized AI model called an embedding model. Now, as the data travels through the layers of this model, it's analyzed at deeper and deeper levels. The first few layers might just spot simple stuff, like edges or colors. But the deeper layers, they start recognizing complex things like a mountain, a tree, or even the overall context of the scene. And what comes out the other end is our vector, that long list of numbers that mathematically describes the image. And as you might guess, it's not a one-size-fits-all kind of thing. There are different models trained for different kinds of data. So you'd use a model like CLIP if you're working with images, but something like GLOVE for text, or even Wave2Vec for audio. Each model is basically a specialist in understanding its own type of data. Okay, this is great. We have our data translated into these meaningful vectors. But now we have a new problem, a big one, a problem of scale. How in the world do you search through millions or even billions of these things super fast? Think about it. Trying to compare your search to every single vector in the database one by one, that would be unbelievably slow. It's not going to work for the kind of applications we're building today. It's totally impractical. So to get around this, vector databases use a really clever shortcut. It's a whole class of algorithms called approximate nearest neighbor, or ANN for short. And that word, approximate, is the key.
Instead of finding the absolute 100% perfect match, ANN algorithms find matches that are super likely to be the closest ones. They trade a tiny bit of perfect accuracy for a massive boost in speed.
And there are a couple of popular ways to do this. One method, called HNSW, is kind of like building a super efficient highway system or a map that connects similar vectors, so you can navigate between them really fast. Another one, called IVF, works by first grouping similar vectors into little neighborhoods or clusters. Then, when you search, it only looks inside the most relevant neighborhoods instead of the whole city. Both are just brilliant ways to find what you're looking for without searching everywhere.
All right, so this stuff isn't just some theory locked away in a computer science lab. No way. This is the actual engine powering some of the most incredible AI tools that you're probably using every single day. Vector databases are absolutely crucial for a process in AI called retrieval augmented generation. You'll hear it called RAG. And to put it simply, RAG is how we give these big language models, or LLMs, a specific library of information to pull from before they give us an answer.
So here's how RAG works, step by step. First, you ask a question. The system then takes that question, turns it into a vector, and does a super fast search through its knowledge base to find the most relevant pieces of information. It retrieves that info, and then it hands both your original question and that extra context over to an LLM. This allows the model to generate an answer that's not just smart, but is also grounded in specific, up-to-date facts. And this is a really big deal because it's what helps stop AIs from just making stuff up. It keeps their answers tied to reality. So when you boil it all down, what's the big takeaway? A vector database gives all our messy, unstructured data a home. It's a place where it can finally be understood, organized, and, most importantly, found based on what it actually means.
You know, this ability to search by meaning, to understand context and similarity at a massive scale, it's not just another upgrade. It's a completely new way of thinking. For decades, we've taught computers to think in neat rows and columns, but now we're finally teaching them to understand nuance, to understand meaning. So the real question isn't just what problems will we solve next. It's what entirely new forms of creativity, of discovery, become possible now that our machines can finally understand, not just our words, but what we truly mean.